All right, it looks like that when I recorded the lecture in the classroom, it was muted. So this is a version with the voice, but I'm going to use my annotated lecture, so this would be shorter. So the first thing we did was to go over Mason's gain formula. If you remember, we used flow graph diagram to convert block diagram to flow graph diagram. So we use the nodes and branches and the gains. Now we do that because we want to find the transfer function of our system. So that's one way. Now here to write the transfer function, T of S, we will say that sigma pk delta k over delta. So that's the formula. Now TS is our transfer function, which is output over input, right? And pk is the paths that we have. So if we have two paths, P1, for example, and P2, here K becomes 2, and we will have two paths. Delta K1 is the cofactor of path PK, piece of K. And delta S is the determinant of our graph or our system. Path is basically starting from your input, going all the way to the output. That will become your path if you remember from the terminology. Delta K, the cofactor, we use the same formula that we use for determinant for the cofactor. There's a slight difference that I'll show you in an example. Now, how to find determinant? Delta will be 1 minus sum of all the different loop gains. So 1 negative all the gains that exist, all the loops that we have, we will put their gains here. So then plus sum of the gain product of all the combination of two non-touching loops. So we'll find two loops that are not touching, find all of them, and then we will sum of their multiplication, the product of them. And then negative sum of gain products of all the three non-touching loops plus four non-touching loops. And if you can see, we are alternating the sign negative, positive, negative, positive. That's all. Now, here was an example that we solved in the class. This is the same example that we wrote the transfer function. And if you remember, we discussed that here I used that big node. If you remember, the node looked like this in the example. So this was 1, and we said that since this is 1, we can combine these two. So now let's say that this is our example. This is our graph. So the first thing that we need to do, so here we want to write the transfer function. First thing we need to do is to find how many paths we have. So here we'll say that we have two paths, going here P1, going here P2 from input to output, that's it. So these paths are without going to the loop, starting from beginning all the way to the end, which is our output. So we have two paths, P1, P2, and our rows there, I multiply the gain when I go to G1, G2, G3, G4. That's a step 1. Step 2 is to find all the loops. We'll see that here we have 4 loops, 1, 2, 3, 4. Now we can, I gave them names, L1, L2, L3, L4, and writing their gains. Now, why we're doing this? Because from the formula that we had, we know that we have to find PKs, delta K, and delta. Now we just found the PKs, and to find our delta K and delta, we're going to use that equation that we have. Now, if you look at this equation, you would know that T of S would be here P1 delta 1 plus P2 delta 2 over delta, right? So we're trying to find that. Now let's calculate delta S, which is our determinant. Delta S, if you remember from that equation, was 1 minus sum of all different gains loops. 1 minus all the loops, L1, L2, L3, L4, right? Then plus sum of the product of two non-touching loops. So see what loop don't touch each other. So start from L1. This is L1. This is not touching L3 and L4. So combination of L1, L3, combination and product of L1, L4 is this one, and then L1 is touching L2 at this point, right? So we would not write that. The next loop is L2. L2 is not touching L3 and L4. So it's L2, L3, L3, L2, L4. That's all the two non-touching loops. Then if you want to write 3 non-touching loops, we don't have them because if we assume these 3 then this one is touching this. So that's it, we're done. We wrote our delta S. So if you want to expand it, you just plug in the value, the gains, and here you have that big determinant. Now here, the next thing you have to find is our cofactor. Now to find cofactor, you will have to find for each path. So you have to find the cofactor for each path. To calculate that, you go along path 1, for example, and then evaluate this delta 1 by removing all the loops that touches that path, that are on that path. So if we look here, this is path 1, L1 and 2 are touching. So we go eliminate these two, the only two left are these. Now, we have to write the delta equation for it. So it will be 1 minus all the loops that will remain, L3 plus L4, right? Then we should have plus all the two non-touching loops, but we don't have any because these two are touching each other. So this will be only 1 minus L2 plus L4, and 1 minus L3 plus L4. Same thing for path 2. Then delta 2 becomes 1 minus L1 plus L2. And if you plug in the gain values, here becomes your cofactors, delta 1 and delta 2. Now, if we write the transfer function from the gain formula, this is what we get. We plug in the value. This is our final transfer function. All right, we solved another example in the class, if you remember. So we wanted to obtain transfer function for this graph or this system. Here we have 3 paths, P1, P2, P3. So P1 is, so you see that the first one from input is 1. So I didn't put them in, well, 1 to multiply all the gain is 1. So 1 times G1, G2, G3, G4, G5, G6. So this is our first path. The second one is 1 times G1, G2, G7, G6. The third one is 1, G1, G2, G3, G4, G8. You get that, right? So these are the 3 paths that we have, P1, P2, P3. Now for the loops, we have more loops here. You can name them however you want, but these are Marine conventions. So we have 8 loops here, and remember that you should find all the existing loops. So the simple ones are here, this one, you can find one, there is one here. And now if you go, there is one, I'm sorry. Wait for this to go away. There's one here, and there is one here, right? So they could have some part in common. So if you write all of those, you see that I have 8 loops. Now we have to find the non-touching loops. So this is easier because as you can see, most of them are touching, right? So we expect to have less non-touching loops. So let's look at this one. So how we have to find how many loops does not touch this loop, which I called L5 for myself. So one is this one, and then there is this big loop. So there will be 2. So L1 doesn't touch L4 or L7. All right, so now that we have the first non-touching loop, let's check the other one, see if we have more. Here, G8, H1 is touching this one, so that's not it. And we have to find what loop is not touching. So it has to be completely touchless. So it is going to be, so for me is going to be L4, which is G2, G7, and negative H2. This one. So these two are not touching each other. So if you can think of, when we say touching, are the nodes that touching, or they would have common branches. So that's 1 for L5, so which was this one. We found 2 L4 and L7 that they are not touching. So that's it. And we don't have more loops that are not touching. So we will stop here. Now, we will start writing our gain formula. So well, we still have to find our determinant. So now the determinant is 1 negative all the loop gains L1 through L8, right? So that's the first one, plus
Now this part is the two non-touching loop. Two non-touching. So we found that the two non-touching, there are only three cases. L5, L times L4, L5 times L7, then L3 times L4. We will write them here, and that's it. There aren't any three, they're not touching, and we're done. Then now we have to write the cofactors. So we'll have three cofactors because we have three paths, P1, P2, P3. Now, if you remember, to find the cofactor, you have to go on the path and eliminate all the loops that touch that path. So our first one was this. And you see that this is our straight path, all the loops are touching. So if we remove all of them, the only thing is left from the equation for cofactor will be 1. So we write 1. For loop 2, my P2 is 1 times G1, G2, G7. So if I eliminate all of them, the only thing I have left is this one. So it would be 1 minus that, 1 minus L5. For L3, L3 also touches all of this was L3. So you'll see that you have all the loops are touching, so you have to eliminate all of them. The only thing I have left is 1. So you see that this cofactor, even though the graph looked complicated, the cofactors are not that easier. So now I'm going to write use again formula, Mason gain formula, write TS, P1 delta 1, P2 delta 2, P3 delta 3, because K is 3. Divide by my determinant. Now you have here the values, P1 times 1, P2 times 1 minus L5, and plus P3 divided by delta S. So just plug in the value to find the final transfer function. Now, if you remember, I explained, to find the transfer function of a system, if you have the block diagram, I usually give you this choice. You can use block diagram reduction, find your transfer function for the whole system. Or you could use this flowcharts and the flow graph. What you will be left is input-output system. So this system is your transfer function. Either way, you can find it, depending on what kind of complication or how complex your system is, you can use that. All right, so we use an example kind of to put everything together, and especially I try to have a state variable, space representation in it, because I realize that not all of you are familiar with. So this example is basically asking you to write the state differential equation for this system, which is an RCL circuit. Now to do that, I divided this into steps to show you how many steps you have to take to get to actually writing this. So first of all, you always have to identify a set of state variable. If you remember, state variable are the variables in your system that changes. Now, if you're in time domain, changes over time. You can tell the past, present, and future of your system. Now, in a RCL circuit, things that vary, one is the current across your inductor, because it changes the time. The other one is the voltage across your capacitor. So VCT and IT, these two are your state variables. These are the variables that change over time. Now, you have also VTO here as your voltage source. Now, this becomes your input because this is the source that gives the voltage to the system. So in the sense of state space representation, we will call VT our input, U, and then IT becomes our X1 and VCT becomes our X2. So that's what we have here. So we have X1, X2, and VT is our U. And if you remember from the state variable equation, we need to find this form. X dot is AX plus BU. So I already found X and U, what they are. I need to find matrix A and matrix B to form X dot. So when you have X1 and X2, then X dot becomes X dot 1, X dot 2, correct? So we kind of also know how that looks like. So we kind of have the format of solution. And that's what is good about the state space representation, because kind of tells you what you're going to have, what format you're going to get. Now, to find matrix A and B, we have to solve we have to write the differential equation. Why? Because we are trying to find the state differential equation. Now, if you remember, we have done this before, so we will write KVL, sorry, and we get this equation. So here VTs are input, ITs are a state variable, DIDT is x dot of 1, and this one is our x2. So I'm going to leave this as it is, but I need an equation for it, right? So I'm going to write VCT is 1 over integral of IT dt. Now, here we have two equations. One is this one is this one. Now we're going to convert them to the state representation. We're going to bring the states in there. So I'm going to rearrange because I know that I have to have x dot equal to ax plus bu, right? So I'm going to put it in this form. So dit dt is x dot of 1 because x1 is it equal to, so I divided all by L because I didn't want to have any coefficient here. So it's 1 over L VT, and this is my U, I'm going to leave it as it is, negative R over L IT is x1 minus 1 over L VCT is x2. So this is now only based on x1 and x2. Now this could be any system, it really doesn't matter anymore. So we kind of went from an RC circuit to a system. Then our second equation was here. So VCT is x2. But then I have 1 over integral of IT. We don't like integral action there. So one way to get rid of that is to get the derivative of the whole thing. So derivative of this x dot, derivative of this 1 over c is fixed, and then this will be eliminated. So I will have v dot c is 1 over c I t, right? So now that is easy to write, which is x dot 2, 1 over c x1. So I have my second equation. Both of these now are based on my state variable. Now we can go and actually write the state variable equation now. So as we said, VT is U. You can change it to U. It's familiar. You can leave it as VT. Just need to know that's your input. So from this, I'm going to form this equation again. Remember that the state variable equation should look like that. Ax plus b, it has to look like that. Okay. Now x dot x2. So our x dot is x dot 1, x dot 2 because our x here x is x1, x2. So this is x dot, this is x, and this is our u. Then becomes A matrix and B matrix, right? Now, we know that mathematically for this to work, this is 2 by 1, this has to be 2 by 2, right? So we know there will be 4 elements in this. Now for the first row, to complete this, let's look at the first equation. So x dot 1 is, whatever is the coefficient of x1 goes here, whatever is the coefficient of 2 goes here. So this is taking care of the first two, and then for u is the coefficient of u. And see what we put VT equal to u, we just change that variable. So that's the first, and then for the second row, we go to second equation because it has x dot 2. So 1 over c multiplied by x1, right? And then nothing for x2 here, so that's a 0, nothing for u, and then, sorry, that is also 0. So here we wrote our state equation. This is important. So state equation done. For output equation, this is a design decision, and you can, as an engineer, depending on what you're controlling, you can write whatever output you want. For example, output is usually a function of input because you have two variables, right? So, sorry, not input, of a state of the system variable. So you have two variables, VCT and IFT. You can say your output, for example, y could be VCT. So VCT is x2, so your y became x2. Now you have to write the state variable for that. So in the class lecture, there are 4 ways of writing the output. I put all 4 of them, so you can follow that, but really it's always depend on who you as engineer that are controlling what you're controlling. You could also say, I'm not controlling anything. So your y becomes 0, your output is 0, right? So you just write 0. Now, the next thing that the question asked was to draw the signal flow diagram. You can draw the signal flow diagram using your equation, right? We could use a set of equation. It's not showing. Back to, okay. So you can use this set of equation to draw our signal flow diagram. Now, we know that we have 1, 2 variable, 1 input, right? So I'm gonna draw 3 nodes, put my variables in there and my input. And again, whenever we have differential equation, when we are drawing the flow diagram, if I have x1 and I know that there is an x dot 1, so there need to be an integral action between x dot 1 and x1. So I put another node x dot 1, and I know there is integral action between 1 over s is integral action. Same thing, I have x2, I know that I have x dot 2, so one node, there's one integral action. So now, from this, now we have all of our nodes, we will start building the equation. So I start building x dot 1. So x dot 1 becomes Vt over Vt times 1 over L. So this is Vt, so 1 over L, right? Then the next sentence is negative R over L times x1. So this is x1, negative R over L. So you see that I just put the negative in the gain. And then the third is negative 1 over L x2. So that was my x2, negative 1 over L2. So now this is the first sentence we had x dot 1 first equation. So I'm done with that. For the second one, I use this. So x dot 2 is 1 over c x1. So this is x1, connect 1 over c. And then that's it. I built that and I'm done. So that will be your full graph deck. All right, so that was for it. You had class participation to do. You got your password in the class. This is an assignment, it's not a quiz. But on the third part, I think I asked you to put down those passwords. So if you don't have the password, or if you use the wrong password, then your assignment would not be graded. All right, thank you. And sorry for not having the voice on the original recording.